the lecture will be shown the twilight of simplified theories, also the end of the Big Bang era and the coming new era of the multiverse. The prospects of interplanetary travel at speeds thousands of times greater than today, even without G-forces, and more will be shown. Stay with us. Welcome! The lecture is an introduction to a series of lectures on the structure of space, elementary particles, all types of interactions, and the concept of time based on many publications including The Theory of Space as their foundation, registered in 2007 and published in 2016 and in 2017. It means that the theory was available much earlier than the data and images obtained from the JWST telescope. To interest you in this lecture, suffice it to say that the space we live in is four-dimensional, not three-dimensional. The universe did not explode. We are not at the center of the universe, and others may even exist. Interplanetary travel at speeds much higher than today by several orders of magnitude, and even without G-forces are possible. The interpretation of the Lorentz transformation is incorrect, what hides for us new perspectives in science and technology. To sum up, the topics discussed in this lecture are interesting for a wider audience. Therefore, exceptionally, in this lecture, we will omit the mathematical calculations available in the cited publications and focus on the essence of the issues discussed. I have to emphasize that as a theoretical physicist, I see other theories as beautiful sets of hypotheses, assumptions, and ideas. Hence, in my lectures, you will not find any negative opinions about them, but rather their deep analyses. Before we start any analysis concerning the structure of the universe, we will set out on a short journey to the most distant galaxies observed by JWST in the small area of the sky between Ursa Major and Bootes called the extended growth strip. Finally, we reach the farthest galaxy by watching an animation provided by Robert Lea based on the JWST pictures shared by NASA. It means that this galaxy is just near the end of the space or edge, or in other words, its boundaries. Those boundaries of the universe, as advocated by Big Bang theory, are closely tied to the early epochs. On the board, we can see some of the furthest galaxies. What is interesting, some of them are bigger by magnitude than our Milky Way galaxy. What has said Michio Kaku needs to revise our cosmology theories, especially Big Bang, because they should have time to create. Let's see what it means that we are observing the uncovered Z12 galaxy just 330 million years after the Big Bang. On the board, we have two axes, one for the age of the universe and another for the distance in the universe in the same units, namely in billions of years. Let's draw some inferences. Firstly, the axis measuring the age of the universe is nothing else like the absolute time. In turn, the position of our galaxy is denoted as 0 on the distance axis. Consequently, it seems that according to the Big Bang theory, our galaxy is near at the center of the universe in the area plus minus 330 million years. Moreover, the red lines marked on the distance axis indicate the boundaries of space, giving us evidence for the existence of space as an entity, because on their left side, space exists, and on their right side, it does not. However, this topic needs further elucidation. To understand the meaning of the postulated edge of the universe by the Big Bang theory, let's watch the famous scene in the movie Truman Show by Peter Weir, based on the scenario written by Andrew Nicol. I had chosen appropriate music for that scene, namely the 7th Beethoven Symphony. The scene reveals the nature of the Truman world and its boundaries. The natural question arises, namely, what are the consequences of the existence of the boundaries of the flat universe? Usually, to prove the existence of a particular entity, we have to be able to touch it, or taste, or smell it. However, in this case, the existence of the edge of the universe implies the existence of space as an entity, because we can distinguish its boundaries. More generally, we can draw some inferences as follows. Interestingly, many philosophers and even physicists denied the existence of space as an entity. For instance, Leibniz, who saw the world through a philosophical doctrine called idealism, was convinced that the matter is nothing else but the colony of souls and its nature is entirely mental. Taking into account such Leibniz approach, we cannot be surprised that space disappeared as an entity and has been reduced to the properties of matter which is entirely mental. From the Leibniz-Clarke correspondence, which took during 1716, we can learn that Leibniz consequently denies the existence of the space because simply it is not needed for God. Also, Newton adduced God wishes as evidences of the existence of space and even time as separate entities, but Newton preferred to follow his critical intuition, then the idealism doctrine, where everything was possible because all were in the mind of God. Now let's start with the hypothesis that the three-dimensional universe is limited and flat in the four-dimensional space, which is advocated by Big Bang theory. The current radius of the flat universe according to the Big Bang theory is equal 46.5 billion light-years. A flat universe means that it is located on a three-dimensional hyperplane, where every point in it is directly accessible from the fourth dimension, just as every point on a two-dimensional piece of paper is accessible from the third dimension. As we can see on the board, the causes of the observed redshift could be as follows: collision with other particles, relativistic Doppler effect, or curved spacetime or curved space. Interestingly, the Big Bang theory assumed that the redshift was caused solely by the relativistic Doppler effect. Therefore, a flat, three-dimensional universe is a mandatory assumption to avoid contradictions, just to make sure that the redshift was not caused by curved space. Consequently, the Big Bang theory is limited by its assumptions. As we have learned so far, the assumption of a flat universe in the Big Bang theory is needed to guarantee that the sole cause of the redshift is related to the relativistic Doppler effect, and thus avoid many contradictions that are not allowed in any theory, because each of them, it must at least be coherent. In short, if space is limited and we simply reject the strange assumption used in the Big Bang theory of a flat universe, we will conclude that the universe has the shape of the sphere shown on the blackboard. Consequently, Our universe immersed in the four-dimensional space is curved, which means that photons will lose energy when covering long distances in such curved space. Please also notice that the four-dimensional Euclidean space has enough place for other universes as well, which is emphasized in the publication The Structure of Space and Its Impact on Interplanetary Travel and Answers to Fundamental Cosmological Questions. It now doesn't matter where an observer of O1, O2, or OK is located, because they will see a similar shape of the universe, but a different area with different galaxy clusters. The surface area at the boundary of a four-dimensional ball of radius RU is volume in three-dimensional space and is equal. Therefore, substituting for S, the volume of a ball in three-dimensional space, and then comparing the two volumes we have. Finally, we knew that the available three-dimensional space at the boundary of a four-dimensional ball of radius ρ in four-dimensional space is equal to the three-dimensional ball with a radius larger by a factor of 1.68. Similarly, by measuring the available surface area at the boundary of a three-dimensional ball, we can find out that it is a circle with a radius twice the radius of the ball. On the blackboard on the left side, you can see the universe immersed in a four-dimensional Euclidean space and the three-dimensional space available on its boundaries. Similarly, on the right side of the blackboard, you see the available surface on the three-dimensional ball placed in the three-dimensional Euclidean space. Now it is clear why we have to multiply the radius of the universe by the factor 1.68 to obtain the radius of the available three-dimensional space on its boundaries. The calculated radius of the universe in the theory of space is equal to the speed of light divided by the Hubble constant. Later in the lecture, we will provide the derivation of this formula. Meanwhile, let's focus on the results obtained and the structure of the space. The radius of the universe RU is shown in green and is equal to 1.2468 times 10 to the 26th power of meters. The radius R3D of a three-dimensional ball with the volume of the available space is shown in blue and is equal to 30.65 billion light-years. The apparent radius of the universe R apparent is equal to 41.44 billion light-years. The radius of the visible area of space R, visible by the observer ON, which is limited because photons do not reach from further areas of space due to the loss of energy, by moving in curved space, is equal to 20.772 billion light-years. The diameter of the visible area of space D, visible by the observer ON, is equal to 41.44 billion light-years. To sum up, from Earth we still see the same area of the universe, but the light reaching us from the most distant galaxies is their image from 20.72 billion years ago. By the way, it should be emphasized that the quoted theory of space does not explain the formation of the universe, but effectively eliminates its expansion, which is why it can be said that our universe is much older than currently expected. From what we have said hitherto, the space is curved, has the shape of a sphere, and is three-dimensional, however is immersed in the four-dimensional Euclidean space, which has plenty of room for other universes as well. However, the question arises, do we live on the boundaries of the four-dimensional ball? The cited theory of space, by attempting to answer this question, introduced the sources reduction principle, which allows us to find out other dimensions. Consider two interacting vortices in a river or a swimming pool. The vortices will be regarded as equivalent to objects which have an electric charge, and the swimming pool as equivalent to space. Moreover, let us assume that the observer of the phenomenon is composed of this type of object. It means vortices, and therefore the observer imagines space as a two-dimensional Euclidean space. The observer describes vortices as interacting two-dimensional objects. This kind of approach leads immediately to the application of a two-dimensional field. By analogy, it could be referred to as an electric field, of which the source is a vortex, and to the statement that there exist two types of objects with a positive or negative charge. Similarly, we can see that the observed by us electrical charges of the elementary particles in the three-dimensional space are consequences of the additional hidden fourth dimension of space. The existence of the fourth dimension in the universe means that its structure is more complex because it is not reduced to the boundaries of the fourth dimensional ball. It means to the three-sphere, but it is a layer on it with a certain thickness, which we will denote as tau. This layer on the fourth dimensional ball has two three-dimensional boundaries called three spheres and is denoted on the figure as Aleph, Beta, and Aleph, Alpha. The calculated tau by the theory of space is greater than 0.894 micrometers. However, the structure of the space is even more complex because inside the fourth dimensional layer, we can distinguish sublayers denoted as Aleph, Beta, Beta, Aleph, Alpha, Beta, and Aleph, Alpha, Alpha. It is visible on the zoomed area denoted as A1. Interestingly, visible vortices beta, gamma 1, and beta gamma 2 in the fourth dimensional space correspond roughly to vortices observed in the swimming pool, but in the three-dimensional space. Now, it is clear that in the cited theory of space, matter is treated as disturbances of space in the form of vortices. Even more, we can see why the photon denoted as gamma classifies as a boson due to its spin, which is the sum of its ends. For more information, please see the chapter entitled Euler Equations in the Fourth Dimensional Space, which is available online, and the chapter on the essence of quantum mechanics. Those remaining vortices visible on the blackboard correspond to quarks. In the brief outline, quantum mechanics uses the oscillations and nutations of moving vortices around equilibrium while approximating them using a matter wave function with wavelengths found using the de Broglie equation. As you can note, vortices connecting the same border hypersurfaces of four-dimensional differential manifold Aleph, Alpha, Alpha are bosons which correspond, as we suppose, to Higgs bosons. If someone is interested in the properties of elementary particles connecting the same boundary hypersurfaces of a four-dimensional differential manifold immersed in four-dimensional Euclidean space, please read the article Geometry of the Dark Matter and Preliminary Analysis of Alpha and Beta Photons Properties Based on Theory of Space. Now we are ready for an in-depth analysis of the concept of time. First of all, please note that space can exist without the passage of time, but the reverse is not possible, because the passage of time refers to matter that requires space. Moreover, to talk about the passage of time, we must observe moving physical objects, or more broadly, elementary particles. Otherwise, it is impossible to measure the passage of time. Similarly, if we hibernate living organisms, the biological passage of time stops. To say something more about time, let's experiment. Consider a simple experiment with two identical balls made of iron falling into two different liquids. For example, water and water glass, also called sodium silicate. As you might expect, when two balls are released simultaneously from the same height into graduated cylinders containing different liquids, we observe different speeds of the balls. The speed in the graduated cylinder containing water glass will be slower than in the other depending on the concentration of the water glass. Now, we compare these two liquids with two different areas of space which have different gravitational field strengths. Of course, instead of falling balls in these two different regions of space, we can observe a transition between two hyperfine levels of the ground state of the cesium-133 atom. The conclusion from the experiment is obvious. The different passage of time depends on the properties of space. No one will say that the reason for the observed different dynamics of phenomena in two different liquids is the different passage of time. The theory of space introduces the definition of local and absolute time as follows. Local time in a given region of space is the property of space which characterizes the dynamics of changes of the observables of objects which can be differentiated in that area. Also, the definition of absolute time is as follows. Absolute time is the time lapsing in a region of space with a strictly defined distance of 0.894 micrometers between mirror spaces Aleph, Beta, Beta, and Aleph, Alpha, Alpha. Ultimately, as explained, the passage of time in a given region of space is a derivative of its properties. If so, the question arises, namely, which specific properties of the space will be different in the inertial reference system K2 moving in relation to the inertial reference system K1. To answer this question, the quoted theory of space introduces a postulate, namely, the postulate of change of orientation of mirror spaces. Contraction of length in the Lorentz transformation results from the greater than zero angles between the normals to the boundaries, mirror spaces, of the systems moving concerning each other. Directly, the postulate shows that the length of rod L, measured in the K2 system, in which it is restful, is constant. This means that the postulate guarantees us the same distances, for example between elementary particles with electric charges, and thus guarantees their stability. Therefore, in figure Aleph, L means a rod projection on the mirror space of the K1 system. It means that measuring the length in the K1 rod L system moving with the K2 system is a measurement of its projection on the support of the K1 system. Directly from the drawing we have, summing up, the ray of light in system K1 has to cover a shorter distance than in system K2. It is why abridged analysis provided in the special theory of relativity can be used in simplified calculations because it uses three-dimensional space and the passage of time based on the properties of four-dimensional space. Therefore, the cited theory of space ends the time dilatation epoch in the Lorentz transformation and frees us from the limited possibilities. In a moment, I will explain why we observe different passages of time in satellites. Please be patient. Thanks to the introduced natural postulate, it was possible to find additional constituents in the famous Einstein equation showing the dependence of energy on mass and speed. The first constituent, denoted as E, delta J, in the equation is related to orientation changes of the angular momentum in the four-dimensional space and is related to the pure kinetic energy. The second constituent, denoted as ES, in the equation is related to the elastic energy of the deformed boundaries of the space. The discovered energy constituents by the theory of space are essential bases for new theories, including new four-dimensional quantum mechanics and the construction of a new type of rocket engine which allows interplanetary travel with a higher speed but higher by several orders of magnitude. Please read, for instance, a new theory entitled New Generations of Rocket Engines, written by the HTS Physics Department. Matter is a form of energy that is clear from the Einstein equation, which has been extended in the theory of space by additional significant constituents related to the pure kinetic energy, deformation energy of the boundary hypersurfaces and rest energy, but only for vortices connecting different hypersurfaces, which allows discovering the nature of all types of interactions, including gravitation. These additional constituents introduced in the theory of space allow us to calculate many properties of space for astronomical objects. What has been done for the selected planets of the solar system and the Sun in the publication entitled The Structure of Space and its Impact on Interplanetary Travel and Answers to Fundamental Cosmological Questions, written by the HTS Physics Department. On the blackboard, we see deformed boundaries by the astronomical object located on the left side and elementary particle. In this case, one vortex marked blue color, and it's pulling down into space areas with a smaller distance between boundary hypersurfaces Aleph, beta, beta, and Aleph, alpha, alpha. The nature of this phenomenon is a consequence of the interaction between vortices, see red arrows, and the boundary hypersurfaces, which have different properties. In summary, the different properties of boundary hypersurfaces Aleph, beta, beta, and Aleph, alpha, alpha, together with the forces F, alpha, beta, introduced by the vortices connecting these hypersurfaces, lead to their deformation and space curvature. The boundaries are not parallel, so we can introduce an asymmetry vector T, alpha, beta, which is the projection of the unit vector n beta onto the plane tangent to Aleph alpha alpha. Summing up, in the cited publication, it was possible to numerically calculate many properties of space by solving introduced equations like those shown on the blackboard. Of course, all calculations are available in the cited publication, so we can focus on some of the presented results, namely, a symmetry vector on the surface of an astronomical object, distance between boundary hypersurfaces tau on the surface of an astronomical object and at its center, the shape of the boundary beta. Our universe is a four-dimensional differential manifold M immersed in a four-dimensional Euclidean space. Furthermore, the manifold M has the shape of a three-sphere, but is deformed in the regions of astronomical objects. At this moment, the natural question arises, namely, how does the shape of space look near the Earth in the four-dimensional Euclidean space? We answered this question in the publication entitled The Structure of Space and its Impact on Interplanetary Travel and Answers to Fundamental Cosmological Questions, and immediately we were in shock. It turned out that we live in a deep valley, as seen on the plaque. In Figure 1, we see the surface of the Earth denoted as a partial differential symbol of the letter O. The radius of the Earth is approximately 6,371 kilometers. It means that from a distance 10 times the Earth's radius, we will see it in a valley more than a kilometer deep. In Figure 2, we can see the shape of the Earth valley. The projection on the Aleph alpha alpha of the 1 meter rod placed on the surface of the Earth will be equal to 1/9500 times 10 to the power of minus 22 meters. The distance between boundary hypersurfaces is nearly equal to 894 thousandths micrometer. Hence, it is clear why the fourth dimension has been hidden so long before us. In the case of the Sun, we have a much larger asymmetry vector on its surface than on Earth due to the greater intensity of the gravitational field. The distance between the boundary hypersurfaces is also smaller. The blackboard shows the K1 reference frame in which we have an observer consisting of vortices marked in white and a rocket row that moves relative to the K1 frame with a speed v created from vortices marked in yellow. The vortices that make up the rocket deform the boundary layers and are inclined at an angle theta, v, depending on their speed v. Directly from the equations presented in the theory of space, we know exactly the inclination of the vortices, which means the elementary particles, see equations 1 and 2, as well as the elastic deformation energy E, S, boundaries, and the energy needed to change the orientation of the vortices E delta J, see equations 3, 4, 5. Photons emitted by the rocket, marked in red, will lose energy when passing through the deformed area of the boundary layer, which is also due to simplified calculations regarding the relativistic Doppler effect. The same rho rocket will stop after time t if the rocket engines have not been used since passing the observer at rest in the K1 reference frame. After time t, photons transmitted from the rocket will have to travel through curved space to reach the observer in the K1 reference frame, which means that they will also lose energy, and the same part of the energy as passing through the deformed area of space while passing the observer in the K1 reference frame, which was shown in the publication entitled New Generations of Rocket Engines. In its original form, Hubble's law relates the shift of the delta lambda line towards the red with the distance r, see equation 6. For v much smaller than the speed of light and using simplified calculations from the relativistic Doppler effect, we have equation 7. Substituting the right side of equation 7 with the left side of equation 6, we have, for small angles, we have equation 9. Replacing the right side of equation 9 with the left side of equation 1, we obtain equation 10. Replacing the left side of equation 10 with the left side of equation 8, we obtain equation 11. Ultimately, we obtain an equation for the radius of the universe. Consider a rocket rho moving with the speed v, shown on the board. If we carefully analyze all the energy constituents in equation 1, which change depending on the speed v, we conclude that a significant part of the energy is needed to change the orientation of the rocket vortices, namely the E delta J term given in equation 3. This is obvious when we plot the relationships from equations 4 and 5 in figure 1. Please note that the vertical axis has a logarithmic scale. By comparing 2 points determined for a speed v equal to 0.01 of the speed of light, which means for v equal to almost 3,000 km per second, we will conclude that the energy needed to change the orientation of the vortexes is 20,000 times greater than the elastic energy of the deformed boundaries of space, responsible for the movement of vortices in space. I didn't say it explicitly, but the movement of vortices is possible by deforming the boundaries of space, not by changing their orientation. Of course, the changes of orientation of space channels deform the boundaries of the space, but the cause of the movement is deformed boundaries of space. So, the question is how to deform the boundary hypersurfaces without changing the orientation of the vortexes to save large amounts of energy. We answered this question in the publication New Generation of Rocket Engines. In a brief outline, we used photons to increase the deformation of the boundaries of space and thin layers to stabilize the orientation of vortices. Details can be read in the cited publication. Imagine traveling to exoplanets at a speed of 0.1 of the speed of light without any overloads due to the stabilization of the vortex orientation. It seems theoretically possible, which means new perspectives and chapters for our civilization. In connection with what I have said hitherto, we introduce the division of rocket engines as follows: jet engines, HTS engines, HTS engines with stabilization. Directly from the definition, jet rocket engines change the orientation of vortices from which the spacecraft is constructed, and as a result of that, the deformation of boundary hypersurfaces changes. On the other hand, rocket HTS engines change the deformation of boundary hypersurfaces of the spacecraft, which results in a change in the orientation of its vortices. Finally, the rocket HTS engines with stabilization are HTS engines, which by changing the deformation of boundary hypersurfaces do not change the orientation of vortices from which the spacecraft is constructed. One of the functionalities of the GPS, GLONASS, and Galileo systems is to determine the distances R1, R2, R, K between S satellites and O observers based on the position of the satellites and the time that elapses between the transmitted electromagnetic signals from the satellites using atomic satellite clocks, usually rubidium or cesium clocks. Such data is transmitted by satellites to receivers using frames and subframe data. Based on such data, we can calculate the transit time from the satellites to the delta T1, delta T2 receivers, etc., along with the satellite positions. However, to measure the distances r, k from equation 1, we need to know the speed of electromagnetic waves in the atmosphere, which is dependent on the refractive index shown in equation 2. The refractive index n depends on the material, pressure, temperature. Because the GPS signal passes through areas of the atmosphere with different gas content and degrees of ionization, we observe the refraction of these waves. It means their movement is not in straight lines, which is considered when calculating r, k, and adding delays. Moreover, it is important to remember that all these calculations are performed assuming a flat universe, which leads to additional inaccuracies. This means that the measurements will give us longer distances in curved space than in flat space, so we need to reduce delta t, k, which falsely suggests that time passes faster in satellites than on Earth. As you can see, when measuring distances r, k using GPS signals, we encounter many inaccuracies, which lead to the erroneous thesis that time elapses faster in satellites. We know that the passage of time in a given area of space characterizes the properties of space, which are certainly different in a satellite than on Earth. For example, the tau distance between edge hypersurfaces is smaller on Earth than on the satellite. By analogy, it seems that the dynamics of all phenomena on Earth should be greater than in satellites because compressed gas molecules have a higher average speed. Moreover, another reason for the faster passage of time in areas with higher gravitational field intensity is the dynamics of the supernova explosion, because the opposite situation would lead to a contradiction, which means the lack of dynamics of the supernova explosion. This topic requires further explanation, but based on the knowledge provided by the theory of space, I am inclined to the hypothesis that the passage of time is faster in areas of space with a greater intensity of the gravitational field. However, this hypothesis may be wrong, which will not violate the theory of space, because we do not know the impact of the tau distance between the boundaries of space on the passage of time, but we certainly know that such a relationship exists. To sum up, the famous scene from the movie Interstellar, in which the friends meet after a short trip to an exoplanet, could have looked different.